Hello everyone. In this lecture, we will give a brief historical overview of machine learning development and discuss a couple of key points of the data representation relevant for the machine learning study. In this lecture, we will use the materials from MIT Press Deep Learning online books written by Ian Bootfeller, Joshua Bengio, Aaron Corville. If there is no specific figures citation, all figures are extracted from this book. We have learned about AI, machine learning, and deep learning. What's the relation between the three? The turn of artificial intelligence comes early. A program can sense, reason, act, and adapt calculation. This is a so-called artificial intelligence. The idea of creating a machine can compute and doing numerical calculation on behalf of human beings has a long history. Any attempt or approach trying to perform this task can be considered as artificial intelligence. Machine learning is a subset of artificial intelligence. Algorithms whose performance improves as they are exposed to more data over time. We can use a machine try to learn the calculation from the data. Any attempt trying to perform this act can be considered as a machine learning. Deep learning is a subset of machine learning. It uses multi-layer of the neural networks to learn from vast amount of data. It requires more advanced algorithms in order to carry out such a machine learning calculations. In early stage of the artificial intelligence development, machines are developed to perform calculations could be difficult for human beings. With the further development, AI is transformed to work on problems which could be easy for human beings but difficult in terms of formulate questions in mathematical and logical form. The true challenge of the artificial intelligence is to solve problems could be intuitive for human beings but difficult to be formulated and described using logic and mathematical formula. A simple machine learning depends on the representation descriptions. Deep learning quite often involves in complicated calculations based on basic concepts. The performance of machine learning heavily relies on the representation of the data. Take one example. Two groups of data represented in x, y dimension. To classify two groups of data, it could be straightforward for human beings. The blue data are clustered in the center of the xy dimension. The green triangle is distributed around the blue circle. Define the surface boundary between two groups of data is not easy for the Cartesian coordinates. You have to use a curve instead of a linear function. With appropriate mapping, data can be mapped out to the r theta coordinates. With this simple transformation, blue data will be distributed in radius distance closer to the origin, while the green data will be distributed with a larger radius. In the polar coordinates, we can use a linear line to easily separate two groups of data. The process of such mapping is the key of the success of the machine learning algorithms. When we look at the data, each piece of information included in the representation is known as a feature. The extraction of feature is critical for the machine learning development. Here is an illustration of deep learning. We have an image, try to make a classification task, whether this image is a car, a person, or animal. Again, this is trivial for human beings. We can clearly answer immediately it's an image of a person. How can we use a mathematical description of data and pass through a series of the algorithms to give us a classification answer? This is A cartoon to illustrate a deep learning is a multi-layer of a neural network. Each neuron is interconnected with the next layer of a neuron. The input of each neuron will be combined and computed as a weight and passed to the next layer of the neurons. And eventually, we have the output neurons. We can use the value of the weight as a discriminator to report the final classification of the input image. When we look at this input there, the feature is the pixel intensity and also the color. So we have a visible layer. All the pixels will be provided as input. Then we have a 3 hidden layer. Hidden layer is invisible in terms of the output result. The details of the hidden layer determine the complexity of the machine learning algorithms. When you have more than one hidden layer, it requires the advancement of the deep learning calculations. In this example, we have the first hidden layer focus on the edge of the image representation, and the second hidden layer use the information in the corner of the image, and have the third hidden layer with the segmentation capability to look at the object parts. And finally, combine all this information, we have the determination of the type of the image. For different type of learning, there are various components. We can use the nature of this component to classify different type of the machine learning. Without machine learning, we can define a rule-based systems. We have the input features and use the hand-designed program. Based on the prior knowledge, we can build an analytic function to compute the output in order to solve out the problem. Classical machine learning add one more block in this flowchart. Before calculating the output, there's a mapping from the feature. For example, we just map from the Cartesian coordinate to polar coordinate, and using the polar coordinate, it makes the problem easier to solve. In terms of representation learning, the feature can be learned from the algorithms instead of using hand-designed features. If we further just use the simple features, for example, when you have an image, you use every single pixel as an input instead of defining another higher level features as an input, and you rely on multi-layers of the neural networks to resolve the useful features and lead to the final calculation output. This process will be the deep learning. There are 3 historical waves of the machine learning development. Here is a plot based on the frequency of words or phrases being searched in the archive as a function of the years. The result is from the Google Books. You can see 3 waves. The first wave is between 1940 to 1980. And the second wave starts from 1980 to now. And the third wave recently just started in 2016. Is too recent to appear. Therefore, it does not show up in this plot. The first wave can be categorized using the keyword cybernetics. It's the development of theories of biological learning. People introduced the single neuron to describe the brain neuron activities. In 1980s, the development of connectionisms applied on the neural networks with a single hidden layer calculation capability. This technology further developed. In 2016, a boom of the deep learning is enabled because the gradient descent invention. It allows multi-hidden layer calculations and initiate the third wave. We are now just in the rising up phase of the third wave. When we talk about work in machine learning, there are three major types of activities. Applied machine learning means the user who collect data, build models, train models, analyze performance, and evaluate errors. To do one step further, machine learning developers, they are the people who work on implement machine learning algorithms and infrastructure to enable applied machine learning. The machine learning researchers are people who can design and analyze models and algorithms. In this course, we will focus on how to correctly build, train, and analyze. We will focus on being the user who can look at the data, make a choice of the model, train it. We can be a smarter user. With a given input data, we can make a choice of the appropriate model to be built, to be trained, and analyze the result to solve the problem. Through this process, we need to learn about all relevant questions we need to ask and address those questions to work on the machine learning. What is core problems that we can ask on this data? And in order to address that core problems, are all features from the data being available? In particular, is there enough information to learn relationship between the input and output? Whether or not there are prior knowledge for the model assumptions that we should use in order to satisfy all criteria required for the problem. Therefore, feature engineering is crucial as a first step for the machine learning. Quite often, when we get a set of data, we want to apply filtering. We can construct multiple filters, keep only events of interest. As an example, we have a set of sparse events. We can apply the selection, only keep the event with one electron or muon with a transverse momentum greater than 23 GeV. After the filtering, we want to prepare low-level features as a preparation of input for the machine learning problems. Every event is associated to a matrix of particles and features. Take one example. The feature of one event could be form momentum of the first particle and form momentum of the second particle. Each of the form momentum component is a feature for the particle. We can also, with the prior knowledge, we can compute high-level features which can be used which might contain relevant information based on the domain-specific knowledge to solve problems. For example, we might have information per event, which is invariant mass of electron-muon pair. We can take the form momentum information of electron and form momentum information from the muon, calculate the form momentum sum of the two particles, and then calculate invariant mass. High-level features quite often are computed from low-level features. As an example, we can ask the questions how to solve problems without machine learning. To do so, we need to recruit a physics expert to teach you about different physics features. For example, mass peak, color, angular distribution. Here is an example of the proton collisions in Large Hadron Collider. We have particles. It could be a quark. Quark fragmented into multiple gluons, and gluon can further splitting into quark-antiquark pair. Eventually, quark and gluons, they hadronize into color-neutral mesons or baryons, and those stable hadrons can fly some distance, interact with the detector, and provide the useful features can be used for classification problem. In this case, we can ask whether we can classify this produced particle to be a top quark or up, down, or strange quark. That is the light quarks. These three quarks have a much lower mass than the top quark. We could recruit from the domain expert. We can learn top quark is much heavier. When it hadronizes to final state particles, it has more energy to be shared by hadrons. Therefore, we expect there should be more final state particles originating from top quark compared to the light quark. And because there are more particles, there are more spread of the particles. And using such a physics knowledge, we can predict the expected distribution and come out with the best case of the signal process. Here's one example. We can calculate subjectiveness of the distributions. You can read the definition in more detail from the reference papers. Using the known knowledge, we can compute the variables which can be used as a high-level feature for the top quark and the QCD quark jet classification. In this plot, you can clearly see that QCD, that is the light quark jets, U or down or strange quark, can distribute with a higher value of the N subjectiveness, tau 3 over tau 2, while top jets, they distribute with a lower value of tau 3 over tau. Using low-level feature, we can deploy deep learning algorithms to achieve the same top quark versus QCD quark jet classification. Here is an example of the calorimeter cell. Calorimeter measures the energy deposition of hadrons. If we treat it in the image, we can tell top quark jets will have a broader distribution compared to QCD jets with a relatively smaller distribution. Using deep learning, we can directly use this pixelated data for the image classification. To explore the features, we quite often using Python library Numpy and Pandas. Numpy stands for numerical Python. It's the fundamental package for scientific computing in Python. The core data structure is the ND array object. Pandas is built on top of Numpy to manipulate tabular data, such as data stored in spreadsheets or databases. The data structure of Pandas is called data frame. The difference between Numpy and Pandas based on the number of dimensions. The Numpy is a numerical data. It has n dimensions without limitations. It has a less memory consumption, better performance for 50K rows or less data. While Pandas is designed for handling tabular data, it can only handle up to 3 dimensions. It requires more memory consumption. However, it has a better performance For 500K rows or Pandas is more popularly used in the industry right now because it can handle larger rows of data faster and more efficient. In the hands-on lab this week, we will practice the usage of Numpy and Pandas to explore features of the data.